All right, in this example, we're going to calculate a limit numerically. Once again, make sure that you recall what the definition of the limit is, right? The limit as x approaches a of f of x equals L. What that means is that if we take values of x that get closer and closer to a and plug them into this function f of x, then the corresponding outputs are going to get closer and closer to this number L here. All right, in this example, we want to take a look at the limit as x goes to 0 of this function. Okay, this is a rational function. It's a polynomial divided by a polynomial. It's a lot more complicated than the function that we looked at last time. So what I'm going to do in this case is, just to make all of the arithmetic a lot simpler, is I'm going to use a website called Desmos.com. Desmos.com, the URL is just www.desmos.com, and if you go to that site, you'll be here, click on Launch Calculator, and in Desmos you'll be able to type in the function x cubed minus 10x squared plus 31x minus 30 and divided by x squared minus 4. So if you'll notice, as I'm typing in the function, Desmos will typeset it in the way that is easy to tell if you've entered it in correctly or not. So just double check. Let's see, that's the right function. X cubed minus 10x squared plus 31x minus 30 over x squared minus 4. That looks good. I'm just going to, it will also graph it out, but for this purpose of this example, I'm just going to turn it off because all I really care about is the numerical values at this point. So then what I want to do is to create a table. And here I'm just going to put x. So make sure you get rid of the subscript. And then over in this column, I'm going to put f of x here. And so what the table will do, you type in these values for x right here. It will take that number and plug it into the function f here and display the output in that column here. So that's just essentially what we did by hand in the previous video. So we're taking the limit as x goes to 0, right? Limit as x goes to 0. So what I'm going to do is start typing in numbers over here for x that are pretty close to 0, and I will start over on the right hand side of 0 with numbers that are a little bit bigger than 0. So 0.1 is the first number that I plug in, and you can see that's the corresponding y value for it. And then what I'm going to do is just make those numbers get closer and closer to 0. So 0.01 is closer to 0 than 0.1, and then 0.001 is closer to 0 than the others, and then I can just keep following that same pattern and get closer and closer to 0. And you can see the corresponding y values definitely have a pattern to them. They look like they're getting closer and closer to the number 7.5, 7.5. So don't forget, we also need to check what's going on the other side. And so let's just do that with another table. We'll just put another table in here. And again, we'll just call this x. And call this y. Turn that off. Oops, not y, but f of x here. And then now I'm going to start plugging in numbers that are close to 0, but on the left side of 0. And so that would be negative, right? 0.1 is to the left side of 0, pretty close to 0. And then all I really need to do is just make those numbers get closer and closer to 0. So just like I did before, just going to keep adding more zeros in there, and those numbers are closer and closer to 0. And then take a look at the corresponding y values that I have in here, and you can see I've got a similar situation to what was going on over on the right hand side. These numbers are getting closer and closer to 7.5. So the outputs, or y values, are getting closer and closer to 7.5. So it's pretty clear based on the numerical evidence what's going on here. And so what we would say is that the limit as x goes to 0 of this function is 7.5. So in this example and in the previous example, example 1, both of those values that we got were the same as what we would have if we plugged 0 into the function. You can easily check that in Desmos. If you go here and plug in f of 0, and so what that does is just take 0 and plug it in to this function here, and we can see that indeed we get 7.5. So again, you might ask, well, is it always the case that the limit is just what I get when I plug this number in? And the answer would be no, it's not always the case. Although a lot of times it is the case there. So you just have to be careful about how that goes, and we'll look at some more examples, and then later on we'll say a lot more about how that works. So.